Hello everyone, welcome back. In this video, we'll be taking a bit of a look at theorems involving supremum and infimum. So the first theorem states that if A is a non-empty and bounded above set, and the set CA is defined such that CA is C, so the set C capital A is such that it's C small a, where A is all the elements in A. So if the set A is such that A1, A2, A3, then the set CA is C A1, CA2, CA3. Right, and now we're told to show that if we're told to show that the supremum of the set CA is the same as multiplying the supremum of set A by C. Well, let's see if it's true. Let's do the proof of this theorem. So, since we need to show that supremum of CA is C supremum of A, we need to show two things, because the definition of supremum is that it's the least upper bound. So we need to show that C sub A, remember that supremum can also be written as SUP and called as sup, and infimum can be written as INF and can be called as inf. So C sub A is upper bound of CA, and 2, if it is upper bound, then it is the least upper bound. So let's show part 1 first, that it's upper bound. So let A be A in A. Let all the elements A be in the set A, and A is less than or equal to the supremum of A. So A is less than or equal to the supremum of A. Now we're just going to multiply both sides by C. So CA is less than or equal to C sub A. So now we get that C sub A is the upper bound of CA. So we've shown part 1. Okay, let's see what just happened there. So the supremum of A means it is the upper bound of A. So all the elements A are less than or equal to the supremum of A. Now we have multiplied both sides by C, and we get that all the elements in CA are less than or equal to C sub A. So we have shown that C sub A is upper bound. So now we have to show that it is indeed the least upper bound. Then it will qualify to be a supremum. So we need to show it's the least upper bound. We need to show that C sub A is the least upper bound. So let P be an upper bound for CA that is greater than C sub A. So let B be an upper bound. So CA is less than or equal to B. Since B is the upper bound, CA is less than or equal to B. So we get A is less than or equal to B over C. Now we get that B over C is the upper bound for the set A, because it's greater than or equal to all the elements A. So B over C is a upper bound for the set A. So we get that, but since B over C is upper bound for the set A, we get that B over C is greater than or equal to supremum of A, because we have assumed we have assumed that supremum of A exists, and since it's a supremum, it is the least upper bound. We have assumed it for A, and now we have to prove it for CA, for the set CA. So we know that B over C is the upper bound for the set A, and we know that the supremum of A exists. So if B over C is the upper bound for the set A, then B over C is either greater than or equal to the supremum of A, because we assumed the supremum of A is there and it is the least upper bound. So we get that B is greater than or equal to C sup A, and that's what we wanted. So that's what we wanted. So if B is an upper bound for CA, if B is upper bound for CA, then it has to be greater than C sub A. So we have assumed that, so we have let B be an upper bound for CA. So if there's an upper bound for CA, we have proved that it's guaranteed to be greater than C sub A, and therefore we get that, so if B is any upper bound, C sub A will always be less than it. So we have proved that C sub A is the least upper bound for the set CA, and we're done with the proof. So let's take a look at another theorem. So in this theorem, we have to prove that let A be a non-empty and bounded set, and define C plus A as C plus A. The set C plus A is all the elements in A and add C to it, and add C to all the elements in A. So we have to show that the supremum of C plus A is the same thing as adding C to the supremum of set A. So let's see if it is the same. This looks pretty much like a similar proof to the one we did before. So let's follow the same template. So we need to show the definition of the supremum. We need to show that C plus sup A is the upper bound, and if it is upper bound, then it is the least upper bound. So remember this, the definition of the supremum, it is the least upper bound. So if it is upper bound, it has to be the least upper bound for it to qualify being the supremum. So let's do the proof of this. And first let's prove the first part, then we'll go on and prove the second part. So let A be elements in A, and supremum of A be the supremum of A. Supremum of A exists, and it's the least upper bound of A. So A is less than or equal to supremum of A. All elements in A are less than or equal to its supremum. So let's just add C to both sides of the equation. Now we get that C plus supremum of A, and remember that C plus A is the set this is the set C plus A. So we get that all elements in C plus A are less than or equal to C plus supremum of A. So we have just proved that C plus supremum of A is the upper bound. Now we need to show that it is the least upper bound. So let's see how we can do that. So let B be an upper bound. So suppose for contradiction, let B be an upper bound that is greater than C plus supremum of A. So we hope that something strange happens and it isn't possible. So C plus A, since B is the upper bound, C plus A is less than or equal to B. So B is greater than is the upper bound for the set C plus A. So therefore it's greater than or equal to all the elements in C plus A. So C plus A is less than the element C plus A, which is in C plus A. So that's getting really confusing here. So is less than or equal to B, and we can write this as A is less than or equal to B minus C. So B minus C is the upper bound for the set A, right? Because the all the elements in A which are A are less than or equal to B minus C. So B minus C is the upper bound for the set A. Since B minus C is the upper bound, it has to be just like last time. It has to be greater than the supremum of A, because we have assumed right here that supremum of A exists and it is the least upper bound. So if we find any other upper bound, it has to be greater than the supremum of A. So we get this, and we just take C to the other side of the equation. We get C plus supremum of A is less than or equal to B. So our initial assumption that B is greater than C plus supremum of A is wrong. So if there's any other upper bound B, it is definitely less. If it's definitely greater than or equal to our upper bound, our supremum C plus supremum of A. So C plus supremum of A is indeed the least upper bound. If we find any other upper bound such as B or D or E, it will always be greater than C plus supremum of A. So C plus supremum of A is the least upper bound, and we're done with the proof. So you guys try to do the same thing for the infimum for practice. So let's take a look at this last theorem before we end the video. We're supposed to show that suppose S is a non-empty bounded above set. We're told to show that, and negative S consists of the elements, all the elements negative small s which are in S. So we're told to prove that the infimum of the negative of the set negative S is the same as negating the supremum of the set S. So let's see what's happening right here. So the set S is made up of elements S1, S2, S3. The set negative S is made up of the elements negative S3, negative S2, negative S1. So let's follow the same template for the proof. First, we'll show it is lower bound for negative x exists, and if it does exist, we have to show it is the greatest lower bound, because this is an infimum. In the definition of infimum means it's the greatest lower bound. So we have to show it's the greatest lower bound. So let's do the first part of the proof. So let U be the supremum of the set S. We're assuming this. So since it is the supremum of the set S, it is the least lower bound. Things will get pretty tricky right here. Just follow me. Since it's the supremum of the set S, it is the least upper bound. It is the least upper bound. I'm sorry if I said lower bound before. Since now U is the supremum of the set S, I'm going to put U right here. So it's the least upper bound. So if we find any other upper bound for the set S, if we find any other upper bound for the set S, it should be greater than or equal to U, because U is the supremum of the set S. It is the least upper bound. We're assuming this part. So U is greater than or equal to all other elements in S. So U is greater than or equal to S, which is element in the set S. So negative U is less than or equal to negative S. So negative U is a lower bound for the set negative S, because it's less than or equal to all elements negative S in S. So negative U is right here. So we have shown that the lower bound of negative S exists, and negative U is a lower bound for the set negative S. Now we have to show that it is the greatest lower bound. So hopefully we get that negative U is the greatest lower bound for the set S, since we have to show it's the infimum of the set negative S. So suppose for contradiction that there is another element negative V that is greater than negative U. So we get that there's element negative v right here, which is greater than negative u. So we still get that negative v is less than all the elements negative s. We still get that there is an element negative v which is the lower bound of the set negative s. So therefore negative v is less than or equal to all the elements negative s in the set negative s, and we get that negative v is greater than negative u. So let's multiply both these equations by negative, so the inequality sign will switch. So v is greater than s and v is less than u. So I hope you guys see the contradiction right here. So let me explain this contradiction, what's happening here, what's strange which is happening here. In this scenario we're dealing with the set negative s. In this scenario we're dealing with the set s. So we get that negative v is a lower bound for the set negative s, and it is a greater than negative u. But when we switch the signs and and therefore we reverse the inequality sign, we get that v is a upper bound for the set s because v is greater than s. We get that v is a upper bound for the set s because it's greater than all elements s in the set capital S. But we also get that v is a lower bound. It's lower than u. It is a upper bound that is lower than u. And this is a contradiction. This is strange because we just assumed that u is a supremum of the set S, and that's why I emphasized it so much. U is a supremum of the set S, so it's the least upper bound. We said it before, if we find any other upper bound for the set S, it has to be greater than u because u is the least upper bound. But we just found a element v that is a upper bound for the set S because it's greater than all elements S, but it is less than u, which is not possible. So our assumption is wrong. So this assumption is wrong, that our assumption that negative v is greater than negative u is wrong. Therefore if there's any other lower bound, it'll always be the opposite. It'll always be less than negative u. It'll always be less than or equal to negative u. So we just proved negative u is the least, it's the greatest lower bound, and we're done with the proof. So if you guys don't get this proof, please go over it again and see the contradiction. It is a bit tricky to work between two different sets and transporting from one set to the another. So hope you guys enjoyed the video. See you next time.